So maybe I'll start now. Let's see. Yeah, so I'm going to jump right into it today because this is the last talk and I want to get to the punchline. So let me just get into some seemingly technical stuff, and then we'll see where this fits into the big picture. So you've already seen bicategories in Rekha's talks, so I won't define them. So they're a version of two categories, right? They're weak two categories. And the notion I want to focus on is the notion of an adjunction in a bicategory, which is the following data. It's a pair of objects, x, y, a pair of one morphisms between those objects going in opposite directions, and a pair of two morphisms one going from the identity of x to g times f, and the other going from f times g to the identity of y, which satisfy these identities. That if you go from f to fgf by doing f followed by eta, where eta is this thing called the co-unit. This guy is called the co-unit. And here you do epsilon times, oops, this is epsilon times, sorry about the typo. I hope there are no other such typos. Yeah, so epsilon is called the co-unit. And you want this composite, which is a map from F to F, to be the identity two morphism on F. And dually, you have a story for G. Okay, going from G to G, and that should be the identity. So in this situation, you call this an adjunction, this entire data an adjunction, and you say that F is a left adjoint to G and G is a right adjoint to F. Now, here are some examples that you're already familiar with. So if you start with a symmetric, a monoidal category C tensor, then you can produce from this a bicategory which has one object star, such that the morphisms from star to star, that should be a category, that category is C. And the composition of morphisms here is given by the tensor product. So in other words, the objects of BC are the one morphisms of, the other way around. The objects of C become the one morphisms of BC, and the one morphisms of C become the two morphisms of BC, and composition in BC is given by tensor product. And in fact, the data of a monoidal category is essentially equivalent to the data of a bicategory with a single object. So you can ask, if I start with a monoidal category C, I form this bicategory, and then I can ask, take a morphism in this bicategory, that's nothing but an object in C. What does it mean for it to have an adjoint? So here's a definition. You say that if you take an object X in C, you say that it has a right dual if it has a right adjoint when viewed as one morphism in BC. And you say that X is a left dual of Y if X is a left adjoint of Y when viewed as a one morphism in BC. So those are just definitions of what left and right dual mean. So the notion of duals is subsumed. The point of this is that the notion of duals is subsumed by the notion of adjunctions. And that's a useful way to think because of it's not particularly useful for anything at the moment. I've just repackaged the definition, just the same definition that you've already seen in Samik's talk. But this repackaging will be useful for what I need later. So when I work with N categories. Now here's an exercise. So I formulated many things in this talk as exercises. So hopefully that will give you some things to think about. So if C is symmetric monoidal, then if X is a left dual of Y, then it's also a right dual of Y and vice versa. So left and right duals, you don't have to distinguish between them. First of all, there's a statement I've not written down, which is that if an adjoint exists, it's unique up to isomorphism. So if a left dual exists, it's unique up to isomorphism, and if a right dual exists, it's unique up to isomorphism. And if you're in a symmetric monoidal category, you can swap objects. So left and right duals coincide. And the second part of the exercise is to check that I've just repackaged. All I've done is just linguistics. I've just rewritten what Samik actually talked about when he talked about duality in the stable homotopy category. Okay, so that's one class of examples of adjoints coming from monoidal categories. Now here's another class. You take B to be the bicategory of categories, where the objects are categories, the one morphisms are functors, and the two morphisms are natural transformations. then an adjoint pair in this bicategory is nothing but the usual notion of an adjunction of categories. Namely, this exercise asks you to check that giving an adjunction in the sense I defined here as some arrows satisfying some triangle identities is equivalent to the usual thing that you might be more familiar with from, say, basic algebra or something, or even topology, where you say that a pair of functors are adjoint if they satisfy this equation, that hom fxy is the same as hom x2gy. So this is an exercise in like representable functors, and it's, I mean, it's standard stuff if you know some very basic category theory, or even if you don't, you can figure it out. It's elementary. So this is sort of the motivation for calling this adjoint pairs. You might be familiar with adjoint functors. This is a generalization of adjoint functors. And it also contains the notions of duals. So two notions you might be already familiar with, adjoint functors and dual objects are special cases of adjoint pairs in a bicategory. Now repeat this exercise to try and understand what does an adjoint pair look like for the bicategory, which is you take, I think I didn't say what this is. These are large DG categories, presentable DG categories. Maybe I should actually share a screen. I added some notes to the last lecture. Just give me a second. Hope opening it in two screens doesn't cause any issues. Okay, let me just swap screens for just 1 second. Here we go. And we'll swap here. So this is from last time's talk. I just added some notes to it because this is the natural place to add it. So roughly, what is a presentable category? A presentable category is, roughly speaking, modulo some set theoretical things that I'm not saying here, is a category C, a large category C, which has all colimits, which is the end objects of its compact objects. So given a large category, you can look at the compact objects, which you've heard a lot about in this winter school, and you can take end objects in that, which are formal filtered colimits of compact objects, right? And a category is presentable if you can recover it as end of its compact objects, roughly speaking. And why are presentable categories interesting? So when I'm talking about categories now, I really mean infinity one categories. So if often I won't keep saying infinity one. If I say category, typically means infinity one category. So I'm talking about, there is a version for ordinary categories as well. And it formally looks the same. So, so for example, for a large DG category, it makes sense to say that it's co-complete and it's end of its compact objects, and then you say it's presentable, okay? And what is an example of that? For example, if you take the derived category of quasi-coherent sheaves on a scheme, that is the end objects in its perfect complexes. Or in the perfect complexes are like thick of OX, yes. Yeah, but in any case, perfects is, my definition is that they're compact objects in DQ co of X, and DQ co of X is end of perfects. Now, why are presentable categories interesting? They're basically interesting because you have an adjoint functor theorem. So there's a version for one category that's a very old theorem. I don't actually remember who it is due to. But there's a version for infinity one categories that's due to Lurie. And basically it says that if you have presentable categories, then a functor G has a left adjoint if it is if it satisfies some technical condition called being an accessible functor, which I won't get into. But the key point is that if it preserves small limits. So every functor that is reasonable, that is accessible, whatever that means, and preserves small limits, has a left adjoint. Now it's very easy to see that if a functor has a left adjoint, it must preserve small limits. So this is saying that the converse is also true under some technical hypothesis that this functor is accessible. Okay, so this is why presentable categories are important, because if you look at continuous functors between presentable categories, they automatically have adjoints. And this notation that I'm using is that PRLK is an infinity two category whose objects are presentable K-linear infinity categories. So these are like large, if you prefer DG categories, you can think of them as co-complete DG categories that are end of their compact objects. And the mapping space I define them to be functors f c to d that have right adjoints. And by a version
the adjoint functor theorem doesn't need to preserve co-limits.
Here I was saying that the G needs to preserve limits to have a left adjoint.
Oh, okay.
There's
So
a
G
dual,
is the right adjoint.
Yeah, G is the right adjoint. And the dual version is that if F preserves co-limits, then it has a right adjoint. So I put that second version of the theorem into this definition, that functors F C to D that have right adjoints are the same as co-limit preserving functors between presentable categories. And I could also formulate this as, the other way around using right adjoints, but then the maps will point in the wrong direction. So I wrote it this way. Okay. So this is the category is going to play an important role today. And these are the mapping spaces. Important to remember that the mapping space, the mapping space is actually a category. It's an infinity one category. And it consists not of all functors, but as Samik pointed out, of functors that preserve colimits. And those are exactly the ones that have right adjoints by the adjoint functor theorem. So basically, the maps here are adjunctions automatically, because the adjoint is uniquely determined up to contractible choice. And now you have a functor from K algebras, E1 algebras. When I write alg without any further adjectives, it means E1 algebras. You have a functor from E1 algebras to presentable categories, which takes A to the derived category of modules. So if A is a ring spectrum, this is like A module spectra. If A is a DG ring, remember that this is some category whose homotopy category is the derived category of A. You can model it in many different ways, but that's what I'm calling mod A, to sort of suppress the model. Okay, so that's just notation. And in fact, this functor is fully faithful. So this is basic Morita. I mean, this is in a certain sense, a statement of Morita theory, that the maps between algebras are defined to be bimodules, if you recall. This is how I defined this bicategory of algebras. And these can be identified with colimit preserving functors from mod A to mod B. And the way that works is that you take, I think I wrote that down somewhere else. Let me just go back. The way that works is that you take so how do I define the action of a bimodule? If I'm given a bimodule X, which is a bimodule over A and B, it takes an A module to the B module M tensor AX. So that defines a functor from mod A to mod B. And that gives me a functor, in this way, I've constructed on objects a functor from alg to cat k or PRL, which takes A to mod A, and which takes a bimodule to this functor, which M goes to M tensor AX. So that's the setup, and that's the setup we're going to use in today's lecture. So again, let me stop sharing the screen and share the today's lecture slides again. Okay. So that was because I started using this notation without explanation. So now I can explain this notation. So repeat this exercise. So this exercise said that if B is the bicategory of categories, then adjunctions are given by this sort of data, a pair F and G such that this equation holds. Now, the question is, if I take the category PRLK of presentable categories, presentable infinity K linear infinity one categories, and colimit preserving functors, then that's an infinity two category. It has an underlying bicategory. It's homotopy category, which is basically I take the Hom, recall that this means I take the Hom infinity one categories and I replace them by their homotopy categories. So the Hom infinity one categories become, when you replace them by their homotopy categories, become just ordinary categories. And so I get an ordinary bicategory. So this infinity two category gives rise to this bicategory, ordinary bicategory. And now figure out what adjunctions are here. What does it mean? And what does it mean for alg K? And it's not hard to guess. You basically have to just replace Hom here by the mapping space and replace isomorphism of sets by weak equivalence of spaces. That's roughly speaking. Yeah, I mean, not roughly speaking, actually, that's quite accurate. That's the answer, but check that that's the answer. Okay. So another exercise, which I think Samik already mentioned in his talk, was that if you take the category of vector spaces, then a vector space is dualizable I mean, has duals if and only if it is finite dimensional, in which case the dual is Hom from V to the base field K. And here's a slightly harder exercise, but if you're familiar with derived stuff, derived categories and so on, this might be fun to think about, that if X is a reasonable scheme, part of the question is figure out what hypothesis you want to put in your scheme, then the perfect complexes are exactly the dualizable objects in the derived infinity one category of quasi-coherent sheaves on X. And that's just a comment that this is not true for general stacks and so on, higher stacks, or even ordinary stacks. But you have to be careful about it. You need some condition on the diagonal and so on. You need an affine diagonal and some properties. Okay. So moving ahead, let's come to one of the most important examples of a category where we can talk about duality, namely the categories of Bordisms. So these are categories built out of manifolds. So I'm going to start with a kind of basic version, which is just lives in ordinary category theory, and then we'll upgrade to higher category theory. So this category COB-N is a symmetric monoidal category with tensor structure given by this symbol. You'll see why in a second. So the objects are oriented n-1 manifolds. And Hom from M to N are, these are oriented closed n-1 manifolds. These are closed oriented n-1 manifolds. And then the Homs are manifolds with boundary whose incoming boundary is the first manifold and outgoing boundary is the second manifold, up to diffeomorphism relative to the boundary. Okay, so you identify two cobordisms if they are diffeomorphic relative to the boundary. So I've not drawn too many pictures here. Maybe I should draw one fun picture at the bottom.
Yeah, I think one of the n-1 should be n, or the n+1 should be n.
Oops, yeah, thank you. This should be n. Thanks a lot, Sam. That's wrong. This should be n. Let's see, so if I want COB1, I want these to be 1 manifolds and the boundaries to be 0 manifolds. Yeah, that's right. Yeah, that's COB1. And composition is given by gluing. Okay, so here's a picture in this COB category. So this is a picture in COB2. So here I have, on the left-hand side, I have the empty, the circle. So I have the circle, disjoint union, the empty manifold. Now I have a cobordism from that to the union of 3 circles. That's this union of this this bent cylinder and this cylinder. And then I have another cobordism from another manifold with boundary going from these 3 circles to 1 circle union empty. And that's again given by this cylinder plus this bent cylinder. Okay. So, fine. So that's what your category looks like. And you have this diffeomorphism relative boundary. I don't want to get too much into the technicalities because time is really short, right? And the tensor product is simply disjoint union. So the claim is, exercise again, that M is dualizable and its dual is M with the opposite orientation. This is opposite orientation. And here's a picture of what you have to check. Basically, this is almost a proof, or a picture proof, if you like. What you have to check, you have to write down the evaluation and co-evaluation maps and check that they satisfy the triangle identities, right? So the evaluation map, so I wrote that down here. The unit and co-unit for objects in a symmetric monoidal category are called evaluation and co-evaluation maps. That's just a name for this unit and this co-unit. So, so the evaluation map is this cylinder, the co-evaluation map is this cylinder, and here is one of the triangle identities. So recall we have to check these 2 triangle identities. That was part of the definition. And so here is one of them. That's just this diffeomorphism is one of the triangle identities. And the other one is got by reversing the, sort of drawing the S in the opposite direction. So every object is dualizable. Now, here's a definition due to Atiyah and Siegel. Atiyah and Siegel axiomatized, an idea that came from physics. So in physics, people study quantum field theories, And the simplest quantum field theories to study are what are called topological quantum field theories. And for mathematicians, often what physicists do is not, doesn't look mathematically rigorous enough because they calculate some integrals over infinite dimensional spaces and so on when they compute in these quantum field theories. And those integrals are not always well defined, or at least don't appear to be well defined to us. But in the case of topological quantum field theories, so the adjective topological being the key word here, you can actually axiomatize the properties of topological quantum field theory, and that's what Atiyah and Siegel tried to do. So they gave a definition, and they said a topological quantum field theory of dimension d is a symmetric monoidal functor from Cob d with disjoint union as the symmetric monoidal structure to vector spaces with tensor product. So that's a definition. Now the basic question is, can you describe all d-dimensional topological quantum field theories? Can you compute them? In particular, can you compute this quantity z called the partition function evaluated on any particular cobordism that you pick? In particular, cobordisms, I wrote Cob d here, maybe I should have written n to be consistent, but anyway. So one example of a cobordism is a cobordism from the empty manifold to itself. So every closed D manifold will define a cobordism from the empty manifold to itself. You have empty on the left and empty on the right. So in particular, for every closed D manifold, I should get a number, which is a map from, well, the empty manifold has to get mapped to the unit in this symmetric monoidal category, which is the one-dimensional vector space. Similarly, this empty manifold also gets mapped to the one-dimensional vector space. So this cobordism should be a map from K to K, which is simply a number. So every closed manifold should give you a number, and there should be some way to compute this number by chopping up the manifold into little bits, which is what this the functoriality of Z encodes. This definition of this category and the functoriality of Z says that you should be able to compute this number by chopping up the manifold along codimension 1 pieces in the way I've done in this picture. Okay, so here's an exercise, complete classification of one-dimensional topological quantum field theories in the sense of Atiyah and Siegel, is that one-dimensional TQFT is determined by where it sends Z of, where it sends the point with the positive orientation. So there are 2 points that you can consider. There's the point with the positive orientation and point with the negative orientation. And of course, you can consider disjoint unions of these. These are all objects in Cob1. So the claim is that if I know where my functor, suppose I have a one-dimensional topological quantum field theory, and suppose I know what Z of point plus is, then I can determine everything else. Namely, so here's the sketch of the proof. First you have to show, well, you know that the dual of point with a positive orientation is point with a negative orientation. So if point with a positive orientation gets mapped to a vector space V, then point with a negative orientation must get mapped to the vector space V dual. And the evaluation and co-evaluation maps in the Bordism category, in the cobordism category, must get mapped to the evaluation and co-evaluation maps from V tensor V to K, V tensor V dual to K, and from K to V tensor V dual. So, and essentially there aren't many one-dimensional manifolds. So all zero-dimensional manifolds are just disjoint unions of points and points with the opposite orientation. So, but because this functor is symmetric monoidal, you know where all those guys have to go. They have to go to like tensor products of the vector space you've picked and its duals. And the only thing left to check is what happens to one manifolds. I've already told you what happens to the evaluation and co-evaluation. And we also know what happens to the interval, which is the identity. So the only interesting one manifold is the circle. So let's try to understand what happens to the circle. So point with positive orientation gets mapped to V. Point with negative orientation goes to V dual. These guys go to evaluation and co-evaluation on V and V dual. So this composite goes to EV composed with co-EV, which is, but what is co-EV? It's a map from K, maybe I should write this down here. Co-EV is going to induce a map. So Z of co-EV is a map from K to V tensor V dual tensor V, let's say. And V dual tensor V is endomorphisms of V, end V. And this is nothing but a map which takes 1 to the identity map of V. So when I compose it with the evaluation, I'm basically taking the trace of the identity map, and that's just the dimension of V. So the circle goes to the dimension of V. So this one-dimensional topological field theory, the only interesting information it contains is, it's determined by a vector space, and we know the only invariant of a vector space is its dimension, and that's encoded in the value of the field theory on the circle, the partition function on the circle. Okay, so checking the details of this is an exercise. I'll leave it to you to check that this defines the field theory. And conversely, given any vector space, that there's a one-to-one correspondence. Okay, so now let's go to two-dimensional TQFTs. Here you have a theorem which I think is, it's often described as a folklore theorem. I think it was written down by Rekha. The theorem says that 2D TQFTs, taking values in vector spaces, are the same thing as commutative Frobenius algebras over K. And here the correspondence sends the functor Z to its value on the circle. So earlier we sent Z to its value on the point. Now I'm sending Z to the value on the circle. And this Z of S1 is going to be my commutative Frobenius algebra. It's some vector space, and it's going to be equipped with an algebra structure. So let's see how that is. So first, let me define what a commutative Frobenius algebra is. A commutative Frobenius algebra is a commutative algebra structure on A, given by multiplication M, and a trace map from A to K, which is a linear map, which satisfies, saying that it's a trace map means that it satisfies trace of AB is trace of BA. And it should have the property that this induced bilinear pairing, the pairing of AB defined to be trace of A times B, is non-degenerate. Okay. And observe that the cyclicity of the trace implies that inner product of ABC is inner product of A with BC. That follows from this. Okay, so how do I start with Z and produce a commutative Frobenius algebra? That's an exercise which I'm giving you the hint here. Telling you how it works, and you check that it actually defines a commutative Frobenius algebra. So you define A to be Z of S1. Then by the fact that Z is symmetric monoidal, a disjoint union of copies of S1 goes to A tensor K times. You define the multiplication to be Z of this pair of pants, which is a map from Z of Z of S1 tensor Z of S1 to Z of S1. Hence a map from A tensor A to A. The trace is Z of this cap, which is a map from Z of S1 to Z of the empty manifold, which is K. And the trace is Z of this guy. And the fact that the trace is related to the inner product by the formula I wrote down earlier is the fact that you can factorize this in the cobordism category as this composition. Okay. And the unit is this Z of this one. So exercises to one direction of this theorem that I just wrote on the previous slide is easy to check, and that's an exercise to check that this defines a commutative Frobenius algebra. And the converse direction is not terribly hard, but you have to use the fact that you can decompose any surface using into pairs of pants into these elementary pieces, which all look like one of the guys in this list. And then you can compute Z on this manifold as a composite of Z of these pairs of pants. So that's pretty much the idea of the proof. I hope I gave you a reasonable idea how the proof goes in the reverse direction. The main complication here is that here you have to be a little careful. You can give a heuristic proof, but you have to really show that you have these decompositions and they behave well and so on. So it's still an undergraduate level, it's all undergraduate level mathematics to prove this theorem. Okay. So now the question is, can we go to higher dimensions? Can we classify field theories in higher dimensions? And the problem is that you cannot hope for such a classification simply because if you look at the proofs of the sketch of proofs that I gave for dimension 1 and 2, they both involved the fact that you can break up a 1 manifold or a 2 manifold into elementary pieces, which you can completely list out, where each of the elementary pieces are manifolds with boundary. Now, in general, in higher dimensions, there is no simple list of pieces into which I can break up any higher dimensional manifold, which I can just list as some finite list of data, such that each piece is a manifold with boundary. So the solution to this problem, and this idea is due to Bayes and Dolan, I think, it's called the Bayes-Dolan cobordism hypothesis, the theorem I'm going to state later. I'm not sure, I'm sure physicists also thought about this in a different language. So we'll go with Bayes and Dolan for now, but I think we should also look at the physics literature to see what they had to say about it. Okay, so the solution is to allow manifolds with corners. So if I allow manifolds with corners, then I can take any higher dimensional manifold, and for example, I could triangulate it, and each of the pieces would be like a simplex, which is a manifold with boundary and with corners, and that's something that we can completely understand. There's just a there's just one kind of simplex, or even if I allow some kind of tessellations, I can allow just finitely many shapes. So that's roughly the idea. So you allow manifolds with corners, and that puts you in the world of higher category theory automatically. Because if you want to now decompose your manifolds, not just in one direction by chopping, so that you have compositions, but you want to allow manifolds with corners, then you're allowing yourself to break it into pieces which have to be put together in many directions. You don't just put it together linearly to get your manifold, but you have to glue your cubes or simplices or whatever they are in many different directions to put together your manifold. And that's why that involves an N category, a higher category, which has different notions of composition and different notions of morphisms. So what we're going to do is replace Cobb N, which is a category, by something called Baud N, which is an infinity N category. And you've already seen what that is in Rekha's talks. Let me just quickly recall the heuristic ideas that this is a higher category with K morphisms for all K from 0 to infinity, with the property that K morphisms are invertible up to homotopy for K bigger than N. There are many concrete models for what these are. For example, one convenient model to work with is that of n-fold complete Siegel spaces, which are fibrant objects for a certain model structure on n-fold simplicial spaces. So functors from delta cross delta cross delta n times 2 spaces. So in Rekha's talks, you saw one-fold simplicial spaces. There's a natural n, you can iterate the process. You can look at complete Siegel spaces and then ask for simplicial objects in complete Siegel spaces. So you replace spaces by complete Siegel spaces and repeat the process. Look at simplicial objects in complete Siegel spaces and then ask for them to satisfy a Siegel type condition and iterate the process. So it's a non-trivial fact that you can iterate this process and construct a theory of n-fold complete Siegel spaces to get a good model for infinity n categories. And that's just one of the models that you can construct. So I won't say anything more technical about what an infinity n category is, except that it's heuristically given by this idea, and that if you are interested in the precise models, you should look up, for example, n-fold complete Siegel spaces or theta n spaces. So now here's a heuristic description of this particular infinity n category, Baud n framed, that is going to replace my category Cobb n. So we fix a number n, and for 0 less than k less than n, we're going to define what it means to have an n framing on a K manifold. And that is the following data. It is the data of a trivialization of the tangent bundle direct sum n minus k. So the tangent bundle has rank k, and you add to it the trivial bundle of rank n minus k, and that should be the trivial bundle of rank n. So this is like trivializing the stable bundle, but it's like with a fix on the dimension. So I can't add an arbitrarily large Rn minus k here. So this is what an n framing is of a K manifold. So the objects, so heuristically, the objects of Baud n framed are going to be n framed 0 manifolds. So what's an n framed 0 manifold? So an example would be a point with an n framing. So it's a trivialization of the tangent bundle, which is just trivial, which is 0. So it's an isomorphism of Rn with itself. So a framing here would be an element of GLN. Okay, a framing of a 0 manifold is an element of GLN. Then one morphisms are one framed, n framed one manifolds with boundary. Two morphisms are n framed two manifolds with corners, which you view as cobordisms between one manifolds with boundary. So if I'm given, for example, a one manifold with boundary would be an interval, I can have two intervals, and the square would be a cobordism between those two intervals. Now a square has corners, right? It's not a manifold with boundary, it's a manifold with corners. And I also have to carry along the framings in this process, all the way up to level n, where the objects are n-framed n manifolds. So they're n manifolds with a trivialization of the tangent bundle. Then n plus 1 morphisms are diffeomorphisms of framed n manifolds. N plus 2 morphisms are diffeomorphisms between diffeomorphisms, so isotopies between diffeomorphisms, and so on and so on and so on. A succinct way to say that is that N morphisms form an infinity zero category. That infinity zero category is the classifying space for N manifolds with corners with N framings. Okay, so that's the heuristic picture. So here's a theorem due to Lurie, and a completely detailed version of that is written down in a work of Kalak and Schambauer, that this data described heuristically can be organized into a complete sequence space, which furthermore can be equipped with a symmetric monoidal structure to give you a symmetric monoidal infinity N category, bored and framed, where the tensor product is given by disjoint union of manifolds. So I think I used the symbol H to C before, but I looked at, it seems I've made the error of defining it afterwards, so I apologize for that. So, I think I defined them for bicategories, but now I'm defining them for infinity N categories. Yeah, that's the issue. So if C is an infinity N category, we can define its homotopy bicategory, if you like, which is defined as follows. The objects are the same as the objects of C. The one morphisms are the same as the one morphisms of C. Now the two morphisms you truncate. So you take equivalence classes or isomorphism classes. I think equivalence is a better word here. Equivalence classes of two morphisms in the original category C. So you identify isomorphic or equivalent two morphisms. So that gives you a bicategory. Okay, so that's a definition. Now, if C is an infinity N category, we're going to make this definition. It might seem like a lot to digest, but I'm going to give you the heuristics on the next page. So for now, this is just to have a formal definition. So you say that C admits adjoints for one morphisms if this homotopy bicategory admits adjoints for one morphisms, which I defined earlier. You say C has duals for objects if the homotopy bicategory of BC, which is defined as before, so the BC is a category with one object, and the morphisms from the object to itself are C itself, okay? And composition is given by tensor product. So this BC is now an infinity N plus one category, and its homotopy 2 category should have adjoints for one morphisms. So recall that one morphisms in BC are objects of C. So we're really asking for duals for objects. And then we ask for 1 less than K less than N. We say that C admits adjoints for K morphisms if for every pair of objects, the mapping infinity N minus 1 category admits adjoints for K minus 1 morphisms. Now that's clearly a mouthful. It's a lot to digest. But I'll give you the heuristics on the next page. So let's just ignore this if it's too much to digest for a second. Finally, I'll make the definition that C has duals. And this entire definition is due to Lurie. That C has duals if C has duals slash adjoints for K morphisms for 0 less than K less than or equal to N. So for zero morphisms are objects. So that's why I have to say duals slash adjoints. So it should have adjoints for 0 less than or equal to K less than N. And strictly less than N. So what does this actually mean? Okay, so I'll come to that in a second. So here's a proposition due to Lurie that if C is any symmetric monoidal infinity N category, then there exists a subcategory C fully dualizable, which has duals and which is universal with this property of having duals, meaning that it's the maximal thing sitting inside C that has duals. Every other category with duals mapping to C factors through C fully dualizable. And we're going to say an object X in C is fully dualizable if it actually lands inside C fully dualizable, if it lives inside this CFD. Okay, that's clearly a lot of stuff in that definition. So what does it actually mean? So here's what it means heuristically. So so take an object X in your symmetric monoidal infinity N category C. You say it's fully dualizable if, first of all, X has duals in the usual sense. So this is literally the sense that you saw right at the beginning in Samik's talk and the sense that I defined it on just duals for objects on the first slide. So X should have a dual. Now, if X has duals, that means there is an evaluation map and a co-evaluation map for that duality. Now, these maps should themselves have left and right adjoints, ev Lx and ev Rx. This is the left adjoint of evaluation, right adjoint of evaluation, left adjoint of co-evaluation, and right adjoint of co-evaluation. Now, those morphisms, it makes sense to ask if they themselves have right and left adjoints, because they're themselves one morphisms in some category, some mapping category between two things. So those guys should themselves have left and right adjoints, and so on, until you reach level n-1. That's concretely, that's a sort of concrete way to think about what fully dualizable means. And it turns out that being fully dualizable is a very strong condition, as you'll see in a moment. It's not an easy condition to satisfy. But let's start with some easy examples. So let's look at board n framed for n equal to 1. For any, so first of all, the claim is that board n frame has duals for all n. And for all n, that's again a theorem of Lurie. Let me say slide 8. Okay, so by default, everything I say is due to Lurie here, but let me just say Lurie. But for some low dimensional cases, you can try to verify it yourself. So for n equals 1, this is essentially this picture that I drew earlier, right? So n framing doesn't mean much. If n is equal to 1, it just means I've trivialized the tangent bundle of this, of all the one manifolds here. Not a terribly interesting piece of data. And so it's this usual diffeomorphisms. Now let's think of board 2 framed. Now being fully dualizable in board 1 framed, it was a condition on k morphisms for 0 less than k less than 1. So that's just for 0 morphism. So it's just a condition on objects, right? So all we have to check is that the objects in board 1 are dualizable, and the objects are just the point and with the trivial framing and the point with whatever framing you want. So that was not too hard. But now if I go to board 2, it already gets more interesting, because board 2 has one more. To check that something is fully dualizable, you have to check that say I want to check the point with the trivial framing is fully dualizable. I have to check not only that the point has a dual, which is the point with some opposite framing, but also that the co-evaluation and evaluation maps have duals themselves, have adjoints themselves. Now the co-evaluation and evaluation maps, remember, these are 2 framed one manifolds, which means that I have a trivialization of the tangent bundle plus R. So the tangent bundle is one dimensional. You have to add R to it, and that should be isomorphic to the trivial rank 2 bundle. So you can visualize this by sort of drawing a framing on the blackboard, like I draw the trivial R2 on the blackboard, and you think of the that framing as sort of going along. You're trivializing the bundle by identifying the tangent direction plus another copy of R with this copy of R2 here via the embedding into the blackboard. Okay, so that's what a true framing is. Now here's a kind of quite non-trivial exercise in terms of imagination. Draw the pictures necessary to convince yourself that the point with the trivial framing is fully dualizable in board 2. Okay, so I've drawn the evaluation and co-evaluation maps here, but now you have to check some condition that saying that these guys themselves have adjoints, and those will amount to drawing some 2-dimensional cobordisms. And here's one of the pictures you have to draw to check that statement. So this is a hint for the kind of things you need to do. You need to do something like evaluation followed by co-evaluation and draw a unit map to the identity map and so on. So you have to draw such 2 manifolds with corners which interpolate between different one manifolds and keep track of the framing. Okay, so now here's the big theorem. This is a very deep theorem which says that you can classify. So you define an extended topological field theory to be a symmetric monoidal functor from board n framed. A framed topological field theory is a functor from board n framed to C tensor. Okay, where C tensor is any symmetric monoidal infinity n category. Now I can take given such a field theory, I can evaluate it on the point with the trivial framing. That gives them a functor from C to the object from topological field theories to objects of C. So the first claim is that it lands in fully dualizable objects. That's just a consequence of the fact that the point with the trivial framing is a fully dualizable object in board. So this functor Z must take it to a fully dualizable object. So it lands in fully dualizable objects. But here's the non-trivial part. So before I come to the non-trivial part, the first statement is that the left-hand side is in fact an infinity groupoid. So a priori it's some infinity n category, but in fact it turns out to be just an infinity groupoid. So it's just a space. And this space is equivalent to the space of fully dualizable objects. So this evaluation functor is an equivalence of infinity groupoids. So what does this mean? This means if I know what Z assigns to the point, I can completely reconstruct what it assigns to any K manifold for K less than or equal to N, K manifold with corners by some gluing procedure. Okay, so it's a highly non-trivial statement, which tells you that you can reconstruct everything. And maybe one other comment to make, which since I didn't have enough time in my slides to fit it in, I'll just make the comment here, is, which slide am I on? 9. That on the left-hand side, you have an action of ON by rotation of the framing. So the fact that you have an ON action here implies a highly non-trivial statement that you have an ON action on the right-hand side as well, a homotopy ON action, because everything is up to, these are weak equivalences of spaces. So that's a highly non-obvious statement, that if I look at fully dualizable objects, there's an ON action on them. It's easy to describe what this ON action is if I look at the case when n equals 1. When n equals 1, this is just dualizable objects in a symmetric monoidal category, and O1 is just Z mod 2Z, and the action is just the action which takes an object to its dual. The Z mod 2Z action simply switches an object with its dual. So the higher notion of dualizability somehow has a much more structure and includes the action of the homotopy ON action. And there's a version of the cobordism hypothesis where I quotient by this homotopy ON this ON action. So that means I've quotiented out the framing, and I have just oriented bordisms similar to the Atiyah-Siegel framework. And then the statement of the theorem is that functors from the oriented bordism category to C tensor are equivalent to homotopy ON fixed points of the fully dualizable objects. Those are also called Calabi-Yau objects, in the O2 case at least. Okay, so this is a very deep theorem. So now let's look at some examples. So the simplest example is you take C tensor to be mod K. So this is like the derived category of K modules, DG version of that, with tensor product, where K is some commutative ring. Then the fully dualizable objects are simply the dualizable objects, and those are the perfect complexes, which sit inside C. And so a field theory is determined by where the point with the trivial framing goes, and that should go to some perfect complex. And then the circle goes to the dimension of that perfect complex, which is the Euler characteristic of the trace of the identity. So there's not much information there. Now let's look at something more interesting. Let's take the Morita infinity to 2 category of DG algebras or E1 algebras over some field K, or if you like, of E1 ring spectra. It doesn't matter actually for what I'm going to say here. And recall that the mapping infinity 1 category was the category of bimodules, the infinity 1 category of AB bimodules. And I'm going to now produce from this an infinity 1 category by simply discarding the non-invertible 2 morphisms. So in other words, I'm going to define this category little alg by replacing the mapping spaces by the infinity groupoid underlying the infinity category of AB bimodules. So this is just the classifying space of AB bimodules. Now, tensor product of E1 algebras makes alg and little alg into symmetric monoidal infinity 2 and infinity 1 categories. Now, here's a fun exercise. Every object in little alg, not in big alg, but in little alg, in the infinity 1 category little alg, is dualizable, and its dual is in fact A opposite, the opposite algebra. Okay. And I have written something wrong here. This should be A tensor A op. So I just, it's an exercise, but I'll give you what the evaluation and co-evaluation maps are. The evaluation map, well, that should be a bimodule from the unit, which is K, to A tensor A op, which this notation is that AE is A tensor A op. Okay? So it should be a bimodule, and that bimodule is simply A viewed as a bimodule from K to A tensor A op. So it's an A viewed as an AA bimodule, but in this way. And the evaluation map is A viewed as an AA bimodule in the other way. It's an AE K bimodule. So the field theory, so by the cobordism hypothesis, a field theory is determined by where the point goes. So the point must go to some DG algebra or E1 algebra. Then the question becomes, the only interesting question is, where does the circle go? Well, the circle goes to what we call the quote unquote the dimension of A, which is to remind you that in the case of vector spaces, what you assign to the circle is the dimension. And that is going to be now a KK bimodule. It's a map from the image of MT is K, from the unit guy to the unit. This S1 is a map from MT to MT. It's a map from the unit to the unit. So its image is a map from the unit in alg k to the unit in alg k, and so it's a kk bimodule. So nothing but a chain complex of vector spaces. So which chain complex of vector spaces is this? So this is going to be the trace of the identity. So what do I have to do? I have to do Z of evaluation composed with Z of co-evaluation. But remember that composition is tensor product in the category alg. So this is A tensor A op with A, which is called the Hochschild complex. If you're working with ring spectra, this would be topological Hochschild homology of the ring spectrum. Now this picture makes something manifest which was not obvious, which is not a priori obvious, that because everything is infinity, formulated in a natural way, diffeomorphisms of S1 must act on dimension of A, must act on whatever invariant I'm assigning to A. And diffeomorphism of S1 is homotopy equivalent to S1. So S1 acts on this chain complex or the spectrum. Now, if I'm working in the world of chain complexes, let's say I'm over a field, then an S1 action on a chain complex is the same thing as a K epsilon module structure. This I mentioned last time. And a K epsilon module structure on HH of A is the same thing as giving where epsilon is in degree 1. So degree of epsilon is 1. This is slide 11. Degree of epsilon is equal to 1. Epsilon squared is 0. And the epsilon action, for those of you who are familiar with Hochschild homology, is given by Korn's B operator. So you could discover Korn's B operator from topological field theory or from physics, if you like. There's a special case where you take A to be commutative. And in this case, here's an exercise. You show that this dimension of A, also known as the Hochschild homology, which is given by this tensor product, is simply this push out. This is related to a question someone asked about what colimits and commutative DGAs are in the first lecture. They're given by tensor products. Co-product push-outs are given by tensor products. So this tensor product is just this push-out. And then I had another exercise to show that S1 is the push-out of a bunch of points. So using that exercise, you can show that this is nothing but S1 tensor A. Okay, so I have a couple of minutes. Maybe can I take another about 5 minutes?
Yeah, sure.
Yeah, thanks. Sorry for going a little over time. So, so if A is commutative, there's a theorem due to Hochschild, Costan, Rosenberg, which also has a beautiful geometric, argument behind it, which I don't have time to do today. But I just want to state the theorem to connect this to geometry and other commutative algebra. So if A is commutative of finite type, then HH of A is the symmetric algebra on the cotangent complex of A shifted by 1. So if you don't know what the cotangent complex is, you can just look at the special case where A is regular. So if you have a smoothness hypothesis on A, then the cotangent complex is nothing but the Kähler differentials. So this is nothing but differential forms associated to A. So Hochschild homology, this dimension of A, this thing that we just got out for free from topological field theory, actually spits out differential forms. So you could discover differential forms if you didn't know what differential forms are from this sort of more primitive thing in some sense. It's something primitive in the sense it's something about the circle. It's just something about how the circle decomposes and about two-dimensional manifolds. So that gives you differential forms. And more generally, for any reasonable scheme, the Hochschild homology of X, which is the Hochschild homology of the structure sheaf suitably sheafified, is differential forms on X. And if it's not smooth, then you have to take the cotangent complex instead of the ordinary tangent complex. And there's also a version for spectra, where then you have to work with topological and equivalent homology, which is basically the cotangent complex in that context. Okay. So let me just do a comment on another example. You could also work with little PRLK, which is the infinity 1 category underlying this big infinity category PRL, infinity 2 category PRLK of presentable K-linear categories. And this is just completely analogous to the case of algebras. You can show that any object C in little PRLK is dualizable in the infinity 1 sense, and its dual is C op. That's an exercise. And the value on S1 is going to be, again, the Hochschild homology of C. And if C is modules over A, then the Hochschild homology of A is the same thing as the Hochschild homology of C. that actually follows from this theorem. That you can prove this. This is an exercise that these two are the same, just using this theorem, cobordism hypothesis. That dimension of A is dimension of C. Using cobordism hypothesis and the fact that ALG mapping to PRL is fully faithful. Now let's do an example where n equals 2. Here's where the fun starts. Or, well, we already had some fun, but maybe more fun. So if you start with an E1 algebra over K, let me make a definition. You say that A is proper if it is perfect, in other words, dualizable as a K module. It's an A module, it should be a K module. Slide 13 as a K module. And you say that it is smooth if A is perfect as an A tensor AOP module. So here's an exercise. Show that A is proper, respectively smooth, if the evaluation map that we wrote down earlier has a right, respectively left adjoint. So this bit is straightforward. If you figure out correctly what the left and right adjoints of evaluation are, I may have mixed up left and right, so I disown responsibility for that. But evaluation having one of the adjoints says that it's proper. Evaluation having the other adjoint says that it's smooth. That's easy to check. Slightly harder is to check that, in fact, A being smooth and proper, in other words, evaluations having left and right adjoints, is equivalent to saying that A is fully dualizable as an object in this infinity 2 category. So A was already dualizable as an object in the underlying infinity 1 category, but being fully dualizable meant that all evaluation and co-evaluation maps have adjoints, and those adjoints have adjoints, and so on. You can make a similar definition for large DG categories, which are presentable. And again, you say that C is smooth if C is dualizable as a C tensor COP module, and C is proper if C has a compact generator, and the mapping spaces are perfect K modules. And again, you can check that C is fully dualizable in PRLK if and only if C is smooth and proper. Now here's the connection to geometry. So let X be a scheme over a field K, let's say. I'm saying over a field to be a little careful. I think you can make significantly broader hypotheses. So then X is smooth, respectively proper in the usual sense of schemes, if and only if this presentable category, derived category of quasi-coherent sheaves, as a DG category, is smooth, respectively proper as an object in PRLK. And furthermore, if I pick a compact generator, E, and I let A be the endomorphisms of E, then X is smooth, respectively proper, if and only if that algebra A, that E1 algebra, is smooth, respectively proper. Because that E1 algebra A is basically, determines the derived category, as we saw last time. So recall that the A going to mod A from ALGK to PRL defines a fully faithful puncture. So we can work with either of these contexts. Either we can work with categories, or we can work with, if our categories have a compact generator, we can work with just DG algebras. So the generality here basically is like dropping the hypothesis that you have a single compact generator. Okay, so this is my last slide. So this is the fun part where we connect to said duality, and then I'll stop. I could say a lot more about how to go to Poincaré duality and Calabi-Yau spaces and so on, but I think this should just maybe pique everyone's interest in this story, and then leave it for the discussion. So so let's say I have a presentable K-linear category, and let's say it's fully dualizable. Then the field theory associated to that will send the point with the trivial framing to C, which could be like the derived category of quasi-coherent sheaves, or whatever your favorite category is, which I might, if it has a compact generator, I might write it as modules over A. If not, it's just some fully dualizable category C. Actually, if it's fully dualizable, it probably has a compact generator. I have to check if that's true, but I think it does. So in that case, well, we saw the circle goes to the Hochschild chain complex. This is not the Hochschild homology. This is the chain complex. Or if you're a topologist, the spectrum. And that comes with the circle action. Now the interval with the trivial blackboard framing goes to the identity functor on C. But there's another framing I could put on the interval, which is I could make the interval twist around itself once. So I could make the framing rotate once. And that gives me a functor S from C to C. Okay? That guy let's give it a name. That's called the Serre functor. Let's say S from C to C. Now, here's an exercise, a property of C. It's not a very, okay, it's moderately hard exercise, I guess, is that this Serre functor is characterized by the following property, that the mapping space between any two objects is the dual of mapping space from those two objects swapped with S put in before X. So maps from X to Y is the same thing as maps from Y to SX, dual. Or in other words, you have a perfect pairing from maps XY tensor maps Y SX to the base field K. Okay. So I hope now you see, I'd formulated Serre duality in this form. If you take the derived category of coherent sheaves, and you take of quasi-coherent sheaves, and you take S to be tensoring with omega x, and you take C to be d q co of x, then you recover Serre duality. Okay, at least Serre duality for dimension 0 case. If you want the for Serre duality for a d-dimensional scheme, there's some twisted version of topological field theory. I have to put some extra structure on the Bordisms, and then this pairing will land in k shifted by minus d, and that will give you the real Serre duality, because here you really want to shift by d. Okay? You want omega x shifted by d. So that's where I'll stop. So what I wanted, the punchline here is supposed to be that this picture that you can draw is the universal Serre automorphism. Representations of that in some other category is given by a topological field theory. And depending on what your target category is, you would get some Serre automorphism of the object in the target. In the case where C is the derived category of quasi-coherent sheaves, this gave me Serre duality. And there are lots of other interesting examples you can look at. And Poincaré duality can be formulated by taking C to be some suitable category that comes from topology and saying that the Serre functor is trivialized. And that extra structure which trivializes the Serre functor is called a Calabi-Yau structure. And that also has something to do with topological field theory, but I'll stop there because I'm way over time.